Hi. So I'm recording for our asynchronous day some walkthroughs of the Desmos graph activities. This one is the words and graphs um, one that we did a little bit a week ago and a little bit on Monday. And a lot of you asked me to just kind of talk through my reasoning for how I think about these. So that's what I'm going to do. So this is the second screen, the one that has both velocity and position graphs and descriptions. So all three of those need to be matched together. I'm going to talk through it, and I have a key so I can tell when I'm right or not, and I know you don't. But um, let's start talking through it. So I think what I'm going to do first is I'm going to kind of sort things. I'm going to put all my velocity graphs in one place so I can think about them, and I'll put my position graphs in one place and my description someplace else. I know there's not a lot of real estate on this screen. Let's see. So velocity and position and description and velocity and position. Okay. All right, so I've got 6 of each kind, and they all do go together in this case. So remember some of the key things. Velocity graph's area, the area underneath it, matches with the values of the position, and the slope of the position graph matches with the values of the velocity. Okay. So if the velocity graph is flat, that means the velocity is constant. And that means because that the position graph should be slanted and straight. Because the slope of the position graph is constant, that means that the velocity graph should be flat. So first, there's another classification I can make here is flat velocity graphs versus not flat velocity graphs. So let me put this one way down there and that there. So now I've got 3 flat velocity graphs and 3 slanted velocity graphs. So those are very different from each other. And then flat velocity graphs have to go with straight line positions, not curves. So this one can't be here. It cannot go along with a straight velocity, with a flat velocity. So this needs to be over there. That needs to be over there. That needs to be there. So you can see all 3 of these position graphs are straight. All 3 of those position graphs are curved. All 3 velocity graphs are slanted. All 3 velocity graphs are flat. I'm not even going to look at the descriptions yet. Okay, so probably some of these already matched. Now we just need to think about them. Okay, so we've got, let's see. This one shows a velocity of 0. You can see that there's a value up at 24. The green line for the velocity is flat and 0. So that means this object is not moving. Okay, I want a position graph that is not moving. There's only one that does that. This one right below it already, which shows that it is at a position of 24 centimeters. So it's at, some people might get confused about this because it shows that it's at a particular position, not down at 0, but it's not moving. Velocity graph being 0 doesn't mean it's not somewhere, it just means it's not changing from that place. So those two go together. Okay, now let's think about these two. So this one shows a velocity that's less than 24 for 3 seconds. This one shows a velocity that is 24 centimeters per second for 3 seconds. So this one's going to go 24 centimeters in 1 second, 24 in the next second, and then 24 more in the third second. That's going to go 24 times 3, 72 centimeters in 3 seconds. Okay. This one's going to go, looks like it's about 1/3 of that, 8, and then 16, and then 24 centimeters. Okay, I need to flip these around. That one goes there, and that one goes there. Let's make these match up. Okay, let me flip this around so that one's on top. Okay, so the reason this works, I've got a velocity of 24 for 3 seconds, so it's going to go much farther than 24 centimeters. This one's got a velocity less than 24 for 3 seconds, so it's going to go, I don't know, but it looks like it's around 8 centimeters per second. So 8, and then 16, and then 24 centimeters total. Cool. So those are all right now. Now let's look at these three. Well, actually, let me go ahead and make the descriptions match for these. So I want ones that have constant velocities or stationary positions. Constant velocity of 24 for 3 seconds. Oh, it's right there. 24 centimeters for 3 seconds. That makes it go 72 centimeters. A car is at 24 centimeters for a time of 3 seconds. That wording may sound a little strange. It is at one position, at the position 24 for 3 seconds. So that one's there. Okay, this description says speeds up to 24. That's a changing speed. That can't be one of these three. That one goes over here. Moving with constant velocity and covers 24 centimeters in 3 seconds. Promising. That's that one. Constant velocity. The velocity graph is flat. It covers 24 centimeters in 3 seconds. You can see that it has covered from position 0 to position 24 in a time of 3 seconds. Those go together. All right, we're halfway there, and it shows me that those three are matched correctly. All right, now let's do the same kind of reasoning for these other ones that are going to be a little bit tougher because the velocities are slanted. Let's see. So this one is increasing from a speed of 0 up to 24, and it takes 3 seconds to do it. Okay, so I want a curved position graph, and the maximum speed is going to be 24, but the speed is always going to be lower than 24 centimeters per second. The way that you figure out how far it's gone total is you calculate the area of this velocity graph. So the area underneath this is this triangle right here that I'm highlighting. Okay. The base of that triangle is 3. The height of that triangle is 24. So let me write that down. So I've got a triangle whose base is 3 seconds, whose height is 24 centimeters per second. The area of that is 1/2 times the base, which is 3 seconds, times the height, which is 24 centimeters per second. That is 1/2 of 24 is 12. 12 times 3 is 36 centimeters. So that particular velocity graph matches with having traveled a total of 36 centimeters. And it has to be curved to get there. Okay, let's look at the rest of those position graphs now and see if one of them works. So seems like it could be either one of those two at the moment. It's definitely not this one because that one only covers 24 centimeters. So it's one of these two because that travels more than. But this one looks like it's a lot more than 24 centimeters, and this one looks like it's around 24 centimeters. So I'm gonna tentatively go with that one. And then we'll see if one of the other ones is problematic and possibly change that. Okay, so let's do the same reasoning for these other ones. This one, we have a triangle. The height is not 24 centimeters anymore, 24 centimeters per second anymore. It's less than that. It's a 3 second. It is a little hard for me looking at this to tell exactly how high that is. I think it might be 8. Maybe we'll have to measure it or something like that, but it's definitely less than 24 centimeters per second. Let's look at this last one and see if this helps. Oh, this one gets to a much higher speed by the end. So I don't know how high that is, but it's much higher than 24 centimeters per second. It actually gets to 24 centimeters per second in the first second. Yeah, that looks like about the first second. And then in the second, it's going to get up to about 48, since this is a constant slope. And then it's going to get up to 72. So this one's going really fast compared to the other ones. That's definitely got to be this one, which gets to position 24 relatively quickly, and then farther than that because it's going so fast. Those go together. So this one I was right. I can tell that I'm right now because of that area, and then that seeming to be a little more than 24 rather than a lot more than 24. And then that means these two go together. Let's see how that makes sense. It travels a total of 24 centimeters in 3 seconds. This one in 3 seconds. Let's see if we can figure out that area. Since we know that it travels 24 centimeters, because the only graph that matches it is one that shows that it travels 24 centimeters, we know that the area has to be 24 centimeters. That triangle, sorry, that was sloppy, has a base of 3 seconds and a height, I think it's 16. Let's see if that's right. So 1/2 times 3 seconds times 16 centimeters per second. 1/2 of 16 is 8. 8 times 3 is 24. That really is 24 centimeters. Okay, so that height is 16 centimeters per second, so it's about 2/3 of the way up. Great. This is all like coming together. Everything's consistent. So that goes with that. All right, we're almost there. I'm going to move these a little bit farther over so we can see them separately. And now we need to deal with the descriptions. So from rest, a cart speeds up to 24 centimeters per second anytime of 3 seconds. So the maximum speed is 24, and it takes 3 seconds to get there. Yep, that's this one. From 0 to 24 takes 3 seconds. From rest, a cart speeds up, covering 24 centimeters in 3 seconds. That's this one. It covered 24 centimeters. It took 3 seconds to do it. It started at rest. It sped up. Everything fits. From rest, covering 24 seconds, speeding up. And that means this one must match here. From rest, a cart speeds up at a rate of 24 centimeters per second for 3 seconds. So it's speeding up from rest. So the upward slope says speeding up. From rest, it starts down at the corner at a rate of 24 centimeters per second. That's the fact that it goes up to 24 on the velocity graph in 1 second. And then it continues another 24 in the next second, and then another 24 in the next second. And then that's consistent with this graph because of how quickly it curves upwards. There we go. And we're good. Okay, so try that yourself. Separate things, think carefully about it. Know that you've got to have velocity graphs match with position graphs, match with descriptions. Try to scramble them up yourself and don't look at this and then try to redo it yourself. And then talk to me if you're still stuck. Thank you.